In the last session, we learned that providing a large number of load increments, or substep, can help solve the nonlinear finite element models. In this slide, we are going to learn more about the substep settings in ANSYS. Selecting the appropriate substep size is critical in a solution. If the substep size is too small, the individual substep may solve well, but reaching the total load applied may take a prohibitively large number of substeps, and hence, the solution time. If the substep size is too large, the solution may not converge, as explained in the previous session. To overcome this limitation, most commercial finite element analysis software provide some form of the automatic load increment schemes. In the automatic load increment, the software chooses some fraction of the total load on the structure. The nonlinear model is solved with a fraction of the load. If model solves within a reasonable number of iterations, the load increment size, or load fraction, or the substep size, is increased. If the model does not solve, or takes a very large number of iterations to solve, the fractional load applied is further divided into a smaller, incremental steps. This act of splitting the applied load increment further into smaller steps is known as a bisection. Normally, the incremental load in the substep is further divided to half in one bisection. Thus the load is applied in the large number of small increments for highly nonlinear models, while a small number of large increments are used in moderately nonlinear models. In the last slide, we saw how automatic load increments can help find an optimum substep size to ensure convergence and reduce solution time. In this slide, we are going to see the ANSYS automatic load increment feature. Automatic load increment in ANSYS can be activated from the Details window of the Analysis settings in ANSYS Mechanical. If we go to the Details window of the Analysis settings, in the Step Controls table, we see a tab, Automatic Time Stepping. By default, the value for this tab is Program Controlled. We can change it to on or off. If we set the automatic time stepping to on, 3 more tabs appear. Initial number of substeps, minimum number of substeps, and maximum number of substeps. Initial number of substeps indicate the number of substeps decided at the start of the solution. If the initial number of substeps is 5, the load will be incremented in 5 equal increments till the final load is reached. Therefore, only 20% of the load will be applied in the first substep. Minimum number of substep indicates the minimum number of steps the solver should take to reach the final load. For example, if the minimum number of steps is 2, then at least 2 substeps will be taken to apply the entire load. Therefore, a maximum of 50% of the total load will be applied in a single substep, while maximum number of substeps indicate the maximum number of steps that a solver can take to reach the total load. For example, if the maximum number of substeps is 20, ANSYS solver will take no more than 20 substeps to apply the total load. Thus, the smallest substep will have a load of 5% of the total load on the structure. Initial number of substeps, minimum number of substeps, and the maximum number of substeps are applicable to the current load step only. If we change the current load step number, we need to verify that the appropriate number of substeps are defined. Recall that smaller substep size causes improved chances of solution convergence, but larger time to reach the full load. While larger substep size helps reach the total load faster, but the chances of solution convergence decrease. Therefore, a small number in a minimum number of substeps tab results in a faster solution, and a larger number in the maximum number of substeps tab results in a greater certainty of convergence. Also, to ensure no confusion, make sure that the defined by tab is set to substeps and not time steps. Although the two definitions are similar, time step is more relevant in the transient analysis, where load changes are time dependent. Most people find it more convenient to define by substep size for the most nonlinear analysis. In case of a time size, small time size would mean smaller substep, and a larger time size would mean a larger substep. In the last slide, we saw various features with automatic time stepping set to on. In certain nonlinear problems, we cannot let the solver decide a load increment or a substep size. For example, we want to calibrate the FE model by comparing the load deformation curve of a rubber from test and simulation. In such cases, we need results at the regular intervals for consistent comparison with the tests. In such cases, we set the automatic time stepping to off. If we set the automatic time stepping off, we see only one tab of the substep, or the time step size. If we specify the substep number as 5, the load will be divided in 5 equal increments, that is, 20% of load in each substep.